Okay, so let's start lecture number 3. So this lecture, I'm going to warn you ahead of time that is going to be a bit dry, in the sense that it's not going to be as exciting as last week, because we are going to do a bunch of calculations. Not hard calculations, but a bunch of them. So for that, first let's start by recollecting facts from the past 2 lectures. So if you have not been here for the past 2 lectures, then these are facts that I'm going to throw at you. So in the first lecture, what we did was we studied 1 plus 1 dimensional Dirac fermions, which we decomposed into psi plus and psi minus. These are called the Weil or chiral fermions, and we saw that in the massless limit of the Dirac fermions, they decoupled, psi plus minus decoupled, and we evaluated correlation functions like this. Plus y was equal to, I have to write this now, was equal to minus I by 2 pi 1 by x minus y minus I epsilon, and something similar for the right moving fermions. 2y by 2 pi 1 by x minus y plus I epsilon. If you were not here, this is a fact. You can check this, not that hard to find. And then we moved on to a boson, specifically a compact boson, and we went into a tangent that was not really necessary for this lecture, but nonetheless we discussed a compact boson and T-duality. So the idea of T-duality was that you have a compact scalar field phi. Compact means phi plus 2 pi is identified with phi, and then we discovered that this had a dual scalar that we call phi tilde, and we derived that phi tilde was also compact for certain consistency conditions to hold, and we saw that T-duality, which is the partition function for some quantity beta, which is like this, 2x, and this was completely equal to d phi tilde e to the I 1 by 2 pi beta square d phi tilde square, which is nothing but 1 by 2 pi beta. And that was T-duality. So the fact that we are going to use from the last lecture in this lecture is the fact that the compact phi has a dual phi tilde. And also at the end, when I tried to describe what's going on, we saw that T-duality works in the spectrum level by exchanging the momentum and winding quantum numbers. So this I did not derive, but it's not hard to derive. In fact, I leave it as an exercise that you can see that J, the conserved current of the compact boson, coming from the symmetry of shifting by a constant, which we derived to be, well, rather I stated to be that gets mapped to, under T-duality, the winding current of the compact dual scalar, and the winding current was 1 by 2 pi epsilon mu nu d nu phi tilde. And remember that this was conserved because of the antisymmetry of the epsilon mu nu, and this exchange was explained in the context of the spectrum of the zero mode, if you remember from last time. If you don't, then under T-duality, the current of the shift current, that is the current due to the symmetry of the compact boson, gets mapped to the wind current. And the wind, remember, counts how many times the field wraps around the space. Okay. So with this recap, what we are going to do next is, as I said, to quantize the boson theory, which we did not do last time. Well, we did the path integral, but did not quantize it. Well, did not quantize it in the sense that we did not evaluate some correlation functions or expectation values. That's exactly what we're going to do today. And as we know, for a free theory, the 2-point function is the expectation value to evaluate. You'll evaluate that for the boson and then compare it with the fermion 2-point functions and see that they match almost exactly. And since a free theory is given by the 2-point function, we will claim that, these two theories are equivalent. That's the idea. But I have to confess that I don't fully understand it. There are some subtle points that I'm still confused about, and I will try to explain that at the end to have a discussion. All right, so any questions so far regarding recap or something?
So in the 1 over x minus y thing, I remember from last time, it's like the plus or minus.
Yeah. I was just lazy. So this is plus. And minus there.
My question was, is that Lorentz invariant then, or is there some?
It's ultimately Lorentz invariant, but in this form, it's not manifestly Lorentz invariant. This is what you do in light cone quantization, for example. Did you take string theory with Peter Arnold?
No, I attended like a couple of the lectures.
Yeah, so you do light cone quantization, in which you go to this precise coordinates, but then you lose Lorentz covariance manifestly, and then in an attempt we have to restore it or show that it's not lost.
Okay.
Any other question? All right, so let's quantize the boson. So quantization it's a usual thing. So we write down the most general solution for the equation of motion and then promote the coefficients to operators. And let's recall that from this action for the compact boson, the equation of motion is nothing but a 2-dimensional wave equation. And the most general solution, well, actually can be decomposed into a left and right moving solution as well. So we can have plus x plus phi minus x plus a zero mode. Right, zero mode is like the constant part of the solution. For example, constant plus momentum times time plus winding times x. that trivially solves this. And this part is clear, right? It's a standard result. If you remember, all you have to do is to write d square in terms of d plus minus, which is nothing but dt plus minus dx, and then this result immediately follows. So the zero mode is going to be a trouble, and it's the reason to most of the subtleties that I still don't understand. So we are going to be a bit clever, quote unquote, to deal with this zero mode. So we could quantize this left and right moving modes. Well, why not quantize this instead? Well, we are quantizing this through this. So this left and right moving modes are particularly interesting for us because in the fermion case, we were looking at left and right modes as well. So what we will do today is to evaluate correlation functions involving these left and right modes. But to avoid the subtlety due to zero modes, we will try to write down, we will first do this, we will just write phi plus x plus phi minus x minus, where the zero mode is also pushed into these solutions. But now write down phi plus and phi minus in terms of the field and its conjugate momentum, and then we can evaluate correlations using phi and pi correlations itself. That's the broad plan that we're going to follow. Is this step clear? All I've done is to just shove this into, to not think about it. If you want a careful treatment, go to Peter Arnold's class, or read Zwieback. Right. So we would like to write phi plus and phi minus in terms of the field and the conjugate momentum. For that, one equation is not enough. We have two things to solve for. We need one more equation. That's where we are going to use the dual field. So we have this equality beta square d mu phi is the same as 1 by 2 pi epsilon mu nu d nu phi tilde. So we will try to plug this here and try to discover how to write phi tilde in terms of phi plus and phi minus. And you'll see why we are keen to write phi tilde in terms of phi plus and phi minus immediately after. So first let's do that. So this equation I can decompose in, use another color or something. In light cone coordinates, I have beta square d minus. So if I put mu to be plus, I can lower it. And when I lower a plus, it becomes a minus. So if it's a d minus and I substitute this in here, phi plus goes away because d minus on phi plus is 0. So I only have phi minus, and that's equal to 1 by 2 pi. If mu is plus, then I have plus minus. So this is minus. I have d minus phi tilde as well as beta square d plus phi plus equal to minus 1 by 2 pi d plus phi tilde. From these two relations, I can see that phi tilde, if I write it as 2 pi beta square phi minus phi plus, that satisfies that, right? I need to get a, if I plug this in here, that works. Can you see this? Yeah. Yeah. So why are we so keen about writing phi tilde in terms of phi plus and phi minus? The reason is again this equation. So from this, if I put mu equal to t, I have beta square phi dot is equal to 1 by 2 pi epsilon tx is 1. So dx phi tilde. But beta square phi dot is something that's familiar. Beta square phi dot from here is the canonical momentum, right? So what we have is dx phi tilde is 2 pi, well, too many pi's, pi, that pi is the canonical momentum. Then I can write phi tilde xt as 2 pi integral from minus infinity to x dy pi yt. Just solve this. Then now I have two equations. I can solve for phi plus and phi minus, right? So phi plus minus is nothing but half phi minus plus 1 by 2 pi b square phi tilde. Now I've achieved my goal to write down phi plus minus in terms of the field and the canonical momentum pi, which is nothing but phi plus minus xt is half phi xt. Maybe there's a minus sign missing. Sorry about that. Did I miss a minus sign? Epsilon superscript tx is minus 1. Is that right? Right? So under epsilon subscript tx is 1. Epsilon superscript tx is minus 1, right? Let's put a minus sign. So that makes it a minus. At least I'm going to take that convention to match with what I have in the notes. 1 by beta square minus infinity to x dy pi yt. Now I can evaluate commutators between phi plus phi minus. Why? Because all I need is a commutator between pi and phi, but that's what canonical quantization gives us, right? Any questions so far? I know that it's a bit dry algebra, but you have to do it. So canonical quantization, that gives us phi xt pi yt for the same t is I delta x minus y. Now let's do some algebra. Let's compute this. It's a straightforward computation given that. Let's do it for fun. So I have two half factors from that. So that's 1 by 4. And I would have one beta square factor, right? Because pi commutator is 0, phi is 0. Only commutator that survives is phi pi, and whenever I have phi pi, I will have a beta square. So that's a beta square. Yeah. Then I have two terms. From the first, I have a phi x t commutator integral minus infinity to y dz pi z t plus minus infinity to x dz pi ct phi y t. Simple enough, right? So these commutators will give me an I. I'm going to pull it out already. So I by 4 beta square, and I have integral minus infinity to y. This commutator is a delta, so I have dz delta x minus z minus, because it's pi phi, integral minus infinity to x dz delta z minus y. Now, what are these integrals? So this integral is almost 0 unless y is greater than x, right? If y was smaller than x, then this delta function will never have a known zero support, so it's 0. If y is more than x, then only then I would have z has a chance to be equal to 1, equal to x, and then I get 1. So this integral results in theta of y minus x. This is Heaviside theta, which is 0 if the argument is less than 0, and 1 if the argument is greater than 0. So whenever y is more than x, I have the integral and it's equal to 1. And here it's the opposite. So I have theta of x minus y. In other words, this is equal to minus I by 4 beta square sine x minus y. The answer is the sine of x minus y. If x minus y is positive, then the answer is only coming from this part, and that's negative. You get the point, right? All right. Do I want to erase? Let's erase this. Any questions so far? So you can imagine that I can evaluate something similar like phi minus x t, phi minus y t, and the answer is going to be almost exactly the same, just up to a sign. So it's going to be plus I by 4 beta square sine x minus y. Exercise. Now let's do an interesting one. What about phi plus xt and phi minus yt? Any guesses? Remember that this is a left mover and this is a right mover. It's an almost good guess. So the good guess is 0 because these are left moving and right moving. But remember that there is the 0 mode that I shoved into. So because of that 0 mode, this is not going to be 0. Had
delta x minus y or something, no?
well, that's too detailed. I just wanted to see if you guys think it's 0. Well, I thought it would be 0, at least. So let's try to evaluate this. Do I want to go through this, or should I just tell you the answer? I'll just tell you the answer because it's going to look exactly the same. It's going to be minus 1 by 5 for beta square theta x minus y plus theta y minus x. Hmm? It's a theta.
No, if you sum them up.
Hmm?
If you sum them up, what is it?
If it sum them up, it's 1.
Oh, yeah, right.
Delta is the derivative of theta. Well, we integrated delta to get theta. Yeah.
No, summing them up and somehow getting delta, but I think
So if I don't have x equal x is not y, then this is always 1, right? Minus I by 4 b square. But when x is y, both are 1, or if you define theta 0 to be 1, both are 1, so this is going to be minus I by 2b square.
that's what I meant by 2 times delta.
Right. So our naive expectation that the left and right movers decouple is incorrect, but we knew that from the get-go because we shoved the 0 mode into.
Why does it, there is some jump at x equals 1?
Yeah, so you have to define this to be half or something to not get a jump.
Well, if you define it to be 1.
If theta 0 is defined to be 1, then when x is y, 1 plus 1 is 2, and there is a jump. And I try to work with the other definition, and later on, this definition gives me the desired answer and not the other one. So I thought I'll be happy with the jump.
So that's actually important. That,
yeah, this factor is in the end important.
Okay. Interesting.
Yeah, maybe I made a mistake, but we'll know in the next lecture that when I redo the calculation again, I might find that this actually already works. In that case, you will have to erase this from your memory. That's all. But for now, let's use this definition and be happy with the jump.
Okay. About like what's the physical equation? Why there is a jump or the mathematical?
Gary's asking a mathematical thing, I suppose.
It's you can think about it graphically, like mathematically, I guess you can't really. I mean, it seems like there's no way the value at that particular point could matter because distributionally, if you want to think about mathematically, it's the same distribution. So that's what's confusing, I guess.
Yeah, so tomorrow I will evaluate, or probably at the end of this, I will evaluate something like this in the context of BCH formula. So I would have something like that. And if I put a 4 here, I will get an annoying factor of I that I don't know what to do with. But all the textbooks says that it's not an I, and they do not do the calculation, and they do not mention this part either. But I feel like they are doing it under the hood, And if I put this in, I get the right answer. That's why I think, we have to be happy with the jump, and this jump turns out to be important too. But wait till.
Makes sense because like you have a commutator with like two things different between them, and if you equate one of them, it's being evaluated differently. Like it doesn't cancel anymore. Well, the other way it does cancel.
Yeah, usually when you put the same points, you get infinities, right? But here we are fortunate to not have an infinity.
On parts of it, you put the same points. You still have plus and minus, so you don't get infinity, but you get something different.
Yeah, so I'm not sure how to explain this jump in physical terms, but from mathematics, it seems like if I use this definition, I can use the other definition, right? Theta 0 is half. Then I can match all of them. Both the answers are the same, but this later on seems to give me an inconsistency. That's why I don't understand it completely. So next lecture, when we get to this point, let's have another discussion probably. Or maybe when I redo the algebra, I find that this was fine, but I'm not sure. I just did the algebra once. Right. Any other questions? That was an interesting, yeah.
Not like normal order away things like the zero mode.
So normal ordering gets rid of the coincident point x equal to y type thing. Yeah, I don't think they want to normal order the zero mode. I don't think you can normal order away the zero mode. Yeah, the UV part, I'm going to do that right now. So, so let's. These are commutators. Let's evaluate some 2-point functions. So let's try to evaluate, something like this. What did I do? What did I do? Yeah, phi minus xt, phi minus y. X and y. So x and y are now two-dimensional objects, just like we do. So as Sid said, when x goes close to y, this diverges. We'll see that it will diverge. To get rid of that, we are going to normal order this. By that, what we mean is we will just subtract away the x equal to y infinity. And let's define this to be G. So to evaluate this, I think it's easier to go back to A's and A daggers. So let's go back to that. So we have phi xt equal to 1 by beta. This is a normalization convention. dp by 2 pi 1 by square root of 2 absolute value of p. This is the energy in 1 plus 1d with zero mass, of course. ap e to the I p dot x plus a dagger p minus I p dot x. And anticipating UV divergence issues, we're going to put a regulator. So if you remember, this is exactly the same regulator that we put for the fermions. Now we can find pi. Pi, remember, was beta squared times phi dot. So that will be, just going to copy this, I beta dp by 2 pi 1 by square root of p by 2 ap to the I p dot x minus a dagger p e to the minus I p dot x e to the minus absolute value of p by 2 lambda. Now if we have phi and pi, we can find phi plus minus from this relation. Sorry, this relation. I'm just going to do that. So phi minus, after doing that, turns out to be 1 by beta integral dp by 2 pi 1 by 2 beta to absolute value of p 1 plus p by p, and rest of the stuff, this stuff. So this, you see, maybe I messed up. Wait a minute. Sorry, phi plus minus is that. Phi plus minus is that. That's right. Right. And for phi plus, momentum is only positive or something like that. Right movers and left movers. So ultimately, what this does is, like the last lecture, phi minus will end up being integrated over only 0 to infinity, because it's 1 plus absolute value p by p, and if p is negative, then 1 minus p by p is 0, and if p is positive, 1 plus p by p is 2, and that cancels with 2, and so on. P to the p dot x plus a dagger p psi p dot x is p by 2 lambda. I don't need an absolute value because it's positive. And something similar for, well, for phi plus, it will be minus infinity to 0, just like, well, did not write it down. We had it similar for the other case as well.
How are we getting phi minus?
From here.
Yeah, but so we have phi, we have pi.
Plug it in, do the integral. And ignore this contribution from minus infinity and so on.
Yeah, but where does it go?
I just throw it out. Yeah. Put a regulator, that's the idea. So. Right, now let's try to evaluate Right, that's what I was trying to explain in the beginning. Maybe I'll explain it again. So we will evaluate all these correlators, and then we will compare it to the fermion correlators, and we'll find that they are the same. And then we'll claim that, oh, this is that. So we are almost there. We just want to evaluate the correlator. That's why I said in the beginning that this is going to be a dry, calculation-driven lecture. But next lecture, we are going to look at physics based on all these calculations, or rather the end result of all these calculations. So let's evaluate g minus x minus y, so which is what's written up there. So let's do it. So phi minus has a beta, so I'll have 1 by beta square, and 2 phi minus means I have two integrals over momentum, and these factors become 1 by 2 root pq. All right, and the regulator is e to the minus e plus q by 2 lambda, and first correlation, well, the only correlation that is non-vanishing is if you pick a dagger from the field on the right and a from the field on the left, right? If I pick anything else, that's gone. So the correlation I have is AP and a dagger Q. Now from the phi minus x, phi minus y part, A of P will contribute e to the IPX, and a dagger Q will contribute e to the minus IQY, Q dot Y, and phi minus 0 square expectation value, x and y are both 0, so it contributes e to the 0, which is 1. Did a bunch of steps together. So this is what's giving me that, and this is what's giving me this. Right? Both of them has this thing in common.
And if you do a P dagger AQ, it
Mhm.
gives the same thing.
Yeah,
You just double it a little.
AP dagger AQ is 0, right? Because AQ hitting the vacuum is 0. So A0 is 0. Likewise, a dagger is 0. That's why this is the only combination that will give you something non-zero. And if you follow up this quantization condition in these two relations, you will find that this is nothing but 2 pi delta p minus q, the standard thing that we have all seen a million times already. Now I can perform one of the integrals. I get beta square 0 to infinity 2 pi e to the minus p by lambda. P and q are the same thing now, by factor of 2 from here. PQ root becomes just p because p and q are the same thing, and e to the I p dot x minus y minus 1. All good? Now this integral can be done, and I'm going to code the result. You can plug it into Mathematica or something, or just take whatever multiplies p as a constant x, and then take a derivative with respect to that x. That integral is easy to do because it's just e to the p something, and once you get the answer in terms of that x, integrate over x. That's it. Do you want me to go through it? Yeah. So the answer is 4 pi beta square. 4 pi, you can clearly see where it's coming from. 2 pi and 2 beta square becomes 4 beta square. And then log of epsilon by epsilon plus I x minus y, where epsilon is 1 by lambda. So this is the answer. Do you want me to, show that this is the answer?
So then
No, not yet there. There are more steps to be taken.
Just like a standard branch cut for the log. Do you ever have to worry about that, or what?
Right. You have a precise I epsilon type prescription here.
If x minus y is
And also, one thing that I will now mention is that this phi field is not well defined, right? Because it's only defined up to 2 pi. So the correlators that we are really interested in are for well-defined operators, and this problem of branch cuts will go away in that stage.
so. If I took if, just out of curiosity, so if I take this A P's and I have the canonical commutation relations for them, and then I take that expression for phi minus, and I calculate that commutative earlier,
You get 0.
you get 0.
Yeah.
Okay.
That's another confusion that I have. I think I think the trick is, A is 0 or A dagger 0 corresponds to the 0 mode part. If you keep that also, I think you'll get the same answer, which is what I guess Peter Arnold did. Not sure. But if you are naive, just like what we were right now.
You're integrating from 0. So
Yeah.
What does this log mean?
Well, you'll take an e to the log and then it'll make sense.
I have like a 2-hour long session with Kevin about that.
Did I mess it up? Yeah, I messed it up. There's a sign here. And likewise, I can evaluate g plus xy, which is everything replaced with plus, and get it to be 1 by 4 pi b square log epsilon by epsilon 1.
Typical for fermions to have 0 modes.
Right. So that's one subtlety. The fermions, when you quantize it, I think you typically enforce an anti-periodicity condition. So then it cannot have a 0 mode because no constant can be anti-periodic. So the bosons have a 0 mode, the fermions do not have a 0 mode. So at the end, I'll discuss it at the end because I have something written on it. Yeah, but I don't understand it fully. That's the honest answer. Right. So we are all troubled with the log. So we'll try to get rid of the log right now. And we'll get rid of that by recalling the fact that phi plus 2 pi n was identified to be phi where n is an integer. That's the whole definition of being compact. So phi is not a single valued field. So this is not a well-defined operator because it's not a single valued field. What would be a well-defined operator is, for example, d phi. Then that gets rid of these constant issues, or something that respects this periodicity, for example, cos phi or sin phi, or in general e to the I phi. These are because this respects this periodicity, and this has a special name, and this comes from string theory again. These are called vertex operators. So we will declare that we are going to be looking at the correlation functions of this vertex operators. One immediate question is, why not d phi then? The answer comes in later, that these vertex operators can create states with interesting windings, whereas d phi turns out to be that creates only states that has zero winding. So to get more, we will use this as our operators of interest. Also, for some reason, string theorists like this because e to the I phi creates asymptotic states.
So this is not a. So the phi's that we were just working with, they're not operators.
Yeah, they are not well-defined operators due to this, but this is. So
I could consider the scalar field that's not compact, right? But still massless or something.
yeah, but only this compact guy seems to work with fermions, I guess.
Oh.
The ultimate goal is to get there, right? To match with the fermion correlators.
Does this decomposition is phi plus and phi minus, or this phi plus and phi minus stuff, does that only make sense as well for the compact case, would you say? Or
no, if it's 2D, you can have left movers and right movers as your solutions, right? Does it have to be? I don't think it has to be compact. That's a property of the D'Alembertian, right? So
what exactly is a vertex operator? Then just e to the I phi, where
phi is whatever phi that we were using. That's it.
I could do that in QFT. Could I do that in QFT?
Yeah. Well, we are doing QFT.
With compactification. Could I?
Or without compactification, you're asking.
I mean, does it make any sense?
In that case, e to the I phi is an operator, but it's a composite operator. This is still a composite operator, but I don't know if that's of any interest to people. Not sure.
And then is there, I forgot, did you explain it? Why it's a vertex operator, or will we see?
No, the name comes from string theory, where it creates asymptotic states, and there is this thing called state operator map in conformal field theory, that all the asymptotic states are in one-to-one correspondence with an insertion of a local operator somewhere. So that correspondence somehow is the reason for the name. It's just a name at this point,
Okay, I definitely don't understand whatever that string theory thing is.
Yeah.
That's fine.
Right. So one extra thing I'm going to do is,
just before we move on to the point, so then in the case of a non-compact massless scalar field, then we would have to worry about the fact that G plus, if the decomposition works, then would we have to worry about the fact that G plus seems to diverge as epsilon goes to 0? Or it's not really well defined, I guess.
yeah, it's not well defined, right? The phi 2-point function is divergent for cutoff going to 0.
For all x and y, or
Yeah, so the 2-point function is, well, all x and y. That's a question. for x equal to y.
Because like here it looks like it does that for all x and y, unless
If you send epsilon to 0, that's what you mean. Yeah. Interesting. Not sure. You have to think about it. You should know this better, right? 2D field theory, 2-point functions.
that should be fine, but the 2-point functions of this phi plus and phi minus I have not seen. Or I guess I haven't seen the second set like a decomposition of the field operators into plus and minus.
Yeah, but even if you do, for example, phi, this has to be like a log, right?
Yeah.
And I'm not sure if it's like this. There's an epsilon bare, right, sitting there. That's the only thing I'm not sure about. Well, this is like log c minus c prime. Not sure where the epsilon is though. Yeah, I guess we can discuss that later. I'm not sure about the answer. Right.
Because yeah, if you take you could separate it as a constant, and then if you were to take differences, that's well defined.
Right. You mean here, right?
Yeah, so if like phi was some difference of g's, right, then the log epsilon term
Cancel, yes. But is it a difference? I'm not really sure about that either. Yeah. Yeah.
But
Right.
we should think about that later.
But this must be in some string theory literature because they deal with this thing, decomposition into left and right modes. Right. So one thing I'm going to do to make this vertex operator better behaved is to do this. That dot 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 means is normal ordering, which all the daggers comes to the left, non-daggers goes to the right. That's it. The standard normal ordering. We did that somewhere there. Yes. Yeah, I cannot do anything. So given that this is our operator of interest, we will try to calculate this. People just drop this dot dot, but I'm just going to keep it because otherwise we may lose a bit of clarity. I phi minus x dot 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 is I phi minus x. Sorry, y dot dot. So why this minus and plus will become clear. So how do we do this? Now we go back to basic quantum mechanics lessons and recall BCH identity. This is equal to e to the a plus b e to the half ab, or it's equal to, I can flip them around, e to b to the a and the cost of a commutator. That's the BCH. Baker, Campbell, and Hausdorff, yeah. And then let's do a simple example that's akin to this to get a feel for it. So let's take, for example, A equal to alpha A plus alpha prime A dagger, B equal to beta A plus beta prime A dagger. Then we are trying to evaluate dot dot A normal order EB. The BCH is not for normal ordered, it's just for a product. But what's normal ordered e to the A? It's just e to the alpha prime A dagger to the alpha A, all daggers to the left and blah blah blah. Same here. So that's a normal ordering, and e to the beta prime dagger e to the beta A. Now I will swap these two using BCH. That gives me to the alpha prime A dagger to the beta prime A dagger to the alpha A to the beta A, and when I swap them I get e to the alpha beta prime. The commutator of AA dagger is 1. Yeah, just numbers. So what is this bit? This bit is nothing but the normal ordered of e to the A plus B. Right? And what's alpha beta prime? It's the expectation value of normal ordered AB. Now let's imagine that we find an expectation value of the left hand side. Then on the right hand side we are finding the expectation value of, so on the left hand side we are finding the expectation value of product of two normal ordered operators, but on the right hand side I just have a normal order operator times a constant. But normal ordered operators, when I find an expectation value I get 1 in this case. Why? Because I always have A's to the right. So if I expand e to the something A, only that 1 contributes, because A will kill the vacuum. Is that clear? So ultimately what we have is expectation value of dot dot I phi minus x dot 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 minus I phi minus y is going to be, due to this expectation value, only this term survives. And recall what this is. This is nothing but that. Right? All right. And let's just plug in what g minus was. I'm going to get rid of the logarithm, and we will get epsilon by, well, you'll still have the branch cut issue because of the power. Epsilon minus x minus y 4 pi beta square. All right, now we're going to do something out of the blue. So this is staring at our face and telling us to set beta square is 1 by 4 pi. That means I'll get 1 there. So that gives me this equal to, if I pull out a minus I epsilon by x minus y plus I epsilon. Now let's look at this and that. If we make the following identification, the correlation functions match. So here there is an unsatisfactory thing, because in this identification itself, the UV cutoff shows up. To get rid of this, I will mention a way in the next lecture. Right. So it happens only at this special value. If you have a compact boson with a radius square equal to 1 by 4 pi, then all the correlation functions of a 2D Dirac fermion can be rewritten in the case of in using these compact bosons. So that's a bit unsatisfactory, I know. What happens for general beta square? That's an immediate question that will be answered in the first part of the next lecture. Okay, now I will, questions. If people don't have questions, I will explain my confusions.
I think my question is in your confusion because I don't see where that thing is a problem.
Which one?
The thing you said that will be a problem at some point.
Oh, this one?
Yeah.
Oh, that's in the next lecture.
Oh.
Yeah. When we derive something called the duality between massive Thirring model and the sine Gordon model. That's the first example. That's where we will set beta squared not equal to 1 by 4 pi tomorrow. And there, next lecture, and there this subtlety will also show up. So I will, yeah.
I have a comment. I think on what we previously said. So I think you're gonna have the epsilon there as well in the numerator
for phi as well.
I think you have to, just by dimensional analysis, dimensional reasons. Right?
Yeah.
So that's interesting. I never thought of that.
Yeah, how to interpret that, I don't know actually. Yeah. Right, so any other questions or comments? So the first thing I want to comment on is the following. So I just showed this, right? So I could have also derived this. Let's not write dot dot phi plus phi minus, right? And if I follow the same steps, I'm not able to show that this is 0, because phi plus and phi minus, as we were discussing earlier, has the different domains for the p integrals. So the delta function will never have a support. So this will be like 1, for example. But the corresponding thing in the fermionic world is psi plus and psi minus. And I feel like this should be 0. If I think of this as creating, should this be 0? Maybe that's my issue. I don't understand this.
One is creating another two, and you like if one creates the second, like you jump up, jump down, kind of looks like one.
No, this creates a right moving particle, right moving antiparticle, and this only does, the other branch of the Dirac cone. So these are not related to each other. So I feel like they commute past each other. So this expectation value should be 0. But I don't see that here somehow. So that's one confusion I have, immediate confusion. So I can maybe physically argue that away. In the next lecture, we will see that this creates a state with winding 1, and this creates a state with winding -1 or something. So it's a overlap between winding 1 and winding -1 sector, which has to be 0. But I cannot calculate it to be 0 somehow using these expressions.
When you're doing it with exponents, if we do exactly the same thing, we end up with exponent minus p plus on the first side, and the other one will be minus. What do you plug instead of p minus?
Right, so we will have to 5 minus 5 plus type thing.
So you do that instead of
yeah. So if I do it naively like this, as you can see, this is 0 to infinity for 5 minus. For 5 plus, it will be minus infinity to 0. So this thing will never have support because p is always positive. Q.
That would be 0.
And yeah. Yeah, so it will give me 1. So I somehow want to get 0. I'm not sure how to get it by K.
That same issue, I guess, right?
Mm-hmm.
The iteration starts at 0.
Right.
0 mode.
Right. The 0 mode is obviously the culprit, but I don't know how to sort it out. But I can argue physically that, oh, this is winding 1 sector, this is winding -1 sector, so they must be 0.
Like that happens when kind of P and Q are equal to each other. Can that thing be somehow canceling out? Like P0?
This thing? Yeah, but the thing is, P and Q can never be equal to each other because the range of the integrals is P going from 0 to infinity. Yes, that's the 0 mode issue. That's the issue, definitely. Yeah. So the 0 mode issue is the issue. I know that, but I don't know how to, rectify it.
For your point to stand, you don't need it to be 0. You need it to be minus infinity. The result, like G
we need it to be e to the minus infinity. Yes.
Plus minus to minus infinity.
Mm-hmm. Yeah. So this I don't know how to derive it unless you take care of 0 mode somehow very carefully, which I don't understand yet. So the next thing is this fermions. When you quantize, you impose something called the Neuer-Schwarz condition. That means that psi plus at the x plus 2 pi, let's say the space is a circle, is equal to minus x. So this is the condition that you impose. Even if you're doing, say, thermal field theory, you'll impose fermions to be antiperiodic at beta periods. So if this is the boundary condition, then you can never have a 0 mode because no constant can satisfy this condition. So the fermions do not have a 0 mode, but the bosons do have a 0 mode. So this left-right separation is not the same in both theories. What do you do? So Peter Arnold did not know anything, so I emailed David Tong himself. So he told me that for this to completely work out, you have to take into account this condition and the other condition, which is called the Raymond boundary condition, and then somehow add this sector with that sector. Or in other words, when you do path integrals for the fermions, normally we do Neuer-Schwarz boundary conditions for the path integral. but somehow you have to add up all possible boundary conditions. Only then you have this bosonization thing, which I don't understand as of now.
What's the second condition?
Ramond condition, which plus.
How do you have both?
You add both, you do this path integral, get the spectrum, the other path integral, get the spectrum, direct sum them, something like that has to be the case. I don't know what he means exactly.
So in the first case, you can't have a zero mode, but what about in the second?
Here you cannot have a zero mode, but here you can have a zero mode. So that's where the zero mode business is coming from. So that's the idea. So it doesn't even end there. It's not that you have to do the Fermi theory with psi to minus psi as a gauge symmetry. You do this path integral with Z2 gauge symmetry. You make it local, and only then the bosonization follows. That's what David Tong told me. I do not understand it. So to understand it, I think I have to study CFT a lot more. And I found this in some books, but that's in chapter 25 or something. I cannot understand what's going on. The reference is
This was
what Z2 gauge theory, right?
Can you do that on a continuum?
Not sure.
I've never
Yeah.
I guess, out that.
So this guy has really good notes in which this is apparently explained, but it's explained, but I did not understand that part.
Because it's not a Lie group, right? So you don't have the principal bundle.
Mhm. Yeah.
I've only seen the lattice.
Right. These people apparently do it for continuum theories as well. I found a bunch of papers by Nathan Seberg, who does things like this. And for this bosonization to be working out exactly, you need to do that gauge theory. These are all paraphrasing from what David Tong told me.
That is crazy.
Yeah.
To speak of gauge theory, I've never thought about it, but I have thought about it a lot. Gauge theory with a discrete.
No, yeah, I've seen it done, but only for like lattice.
But if you can get away with that, then you can get away with a lot of stuff.
But for applications that we are going to discuss, that's enough. So what we are going to do next week is that completely ignore the zero mode issue, because one, I don't understand it. Two, I don't know how to understand it yet. So let's we'll come back to that in 5 years.
Oh, good timing.
Okay, that's it.
Are you done with your work?
Yeah.